I reach airport, if I leave, I start 25 minutes early to my plane time was 0.04. Now with the new evidence that I have obtained, maybe from the news broadcast, that there are no reported accident at this particular hour from the path that I'm going to use or the road that I'm going to use to travel to the airport. If this new information is fed to me, then I know that my likelihood of reaching the airport is going to increase, because there is no accident probably going to take place after this instant. Again, this is a informed decision, and this may not be an accurate one, but my degree of belief for reaching the airport has now been increased from zero point zero 0.04 to zero point zero 0.06. In the percentage term, earlier it was a 4% chance for reaching the airport in time with plan A25 or action A25 rather. Now it is increased to 6% chance of getting to the airport. Now, if you see the next particular statement here, which reads a probability of A25 given no reported accidents at 5 a.m. and maybe my plane is at 5:30 a.m. So this is now a more appropriate information or more accurate information कि currently नहीं accident हुआ है. Okay, ये no reported accident could be a day's time, पूरा पूरा दिन में होगा, पिछले दिन में होगा. ये वाला जो इन्फॉर्मेशन है ये ज्यादा क्लोज इन्फॉर्मेशन है, और इस इन्फॉर्मेशन से मेरा कॉन्फिडेंस और बढ़ता है, मेरा बिलीफ और बढ़ता है. सो बिलीफ इज व्हाट माय कॉन्फिडेंस ऑन the decision, and now it becomes 15% chance of getting to the airport. Again, everything is probabilistic here, so I'm not saying that A25 is true. I'm saying that A25 is true with 15% chance of it being true. Okay, this is what the probability gives you as information. Now this is what is summarized over here in this slide. Sorry, suppose I believe the following. Probability A25 gets me there on time given nothing is 0.05. Probability A90 gets me there on time with certain information is 0.70. Probability 120 gets me there on time is 0.95, and probability A1440 gets me there on time is 0.999. So the 99% chance that I can get to the particular thing. Okay, so now what does the probability theory, how does we include this probabilistic behavior into the decision making process? And for doing that, we use certain thing called as decision theoretic approach. And this decision theoretic approach is a combination of probability theory and utility theory. Now what is utility theory? Utility theory is used to represent and infer the preferences of user for in a particular decision. So utility it tells you how important a decision outcome is going to be, or how useful the decision's outcome is going to be for the agent. So utility theory defines that. Okay, it is something to do with the utility based agents utility function. So utility function there was telling you how happy you are if you took a particular decision. In here also, this utility theory is going to tell you how happy. So it's going to give you a numeric assistant to define your happiness. So 0.999 is 99% you will be happy, or you will be certain for reaching the airport with this particular decision. So this is just a representation. So decision theory approach for decision making involves combination of probability theory plus the utility theory. So these are two theoretical concepts which combined together give rise to decision theory, and we can design a agent design which uses the decision theory, which is called as a decision theoretic agent. Okay, so now to sum up this entire discussion is that uncertainty is definitely there in many real world problem, and there could be multiple ways in which the uncertainty can creep into the decision making process which the agent is involved in AI problems. Next thing that we came across is if we use the uh, standard logic, or if you use the monotonic logic that we are aware of, the predicate or propositional logic and try to model the agent's behavior in the uncertainty presence, then I may be required to uh, have a very lot I have to come up with lot of contingency plans, and those contingency plans, getting those contingency plans ready is a very difficult and tedious process. And many a times, if I'm using the monotonic logic or the standard logic, which does not compensate the uncertainty, it is going to give me suboptimal decisions, which may not be what I require. So, to support this, we need to use probability theory, and the probability theory can tell us the degree of belief on a particular decision that the agent has, and if we are able to use this information in the inference process and in the representation of the logic, then it is going to be more helpful for me to understand how good or how bad a particular plan that I am working on is. And thus we may actually design a reliable, sort of reliable agent architecture, which is called as a decision theoretic agent, which uses probability theory for representation of the knowledge purpose and utility theory for the decision making purpose. So utility theory is going to give you a spin for actually executing or taking a decision. So it is something which is a dynamic thing which will be actually used as an algorithm for decision making, and the probability theory is going to give you the inputs for representation of the knowledge about the world in appropriate manner when there is a sense of uncertainty in the domain of a representative problem. Okay, so that is what is the summarization of things so far. Now we talk about the syntax. Yeah, I hope everything is okay. So now we talk about the syntax of whenever I want to represent the probability theoretic logic. Okay, so now we are going to see if I want to use logic and if I want to use probability theory together, how they come together. Okay, so basic element in probability theory is called as random variable. Okay, very similar to propositional logic, where the possible worlds are defined by assignment of values to the random variable. Similarly, in probability theory also we do the similar thing. So there could be random variables which are Boolean random variables, or they may be random variables which are discrete random variable. Now there is a classical example that is there. You might have learned it in your in machine learning as well, or data mining as well, which is about how we can model the weather in order to play or not, to take a decision to play or not to play. Okay, so डिसीजन थ्योरी में ये एक बहुत अच्छा एग्जांपल है वेदर का. सो दिस वेदर वेरिएबल has one of the four values. Either it could be sunny, rainy, cloudy, or snowy. ओके, सो स्नो लिखा है, स्नोई. सो सनी, रेनी, क्लाउडी और स्नोई, ये चारों में से एक वेदर का वैल्यू हो सकता है. So this particular variable is called as a discrete variable, and there could be a Boolean variable which just says yes or no. So cavity, presence of cavity or absence of cavity. So the problem that I was giving you earlier with respect to identifying whether diagnosing whether a cavity is there or not in a dental expert, by a dental expert, the variable cavity may be having one of the two values. Either the cavity may be present or cavity may be absent. So true or false, it's a Boolean variable. So I may have random variables which are Boolean or random variables which are discrete. Now, whenever I'm defining a random variable, you know a fact that the random variable uh, associates a probability with each of the outcomes. So whether the weather is sunny, rainy, cloudy, or snowy, there will be some probability associated with that particular value. And if I sum up all those probabilities, it is going to sum up to 1, and that is referred to as a probability distribution. Okay, now see how we can form a sentence, a complex sentence in this particular representation is that, so weather is equal to sunny or cavity is equal to false. So you can use the logical connectives in order to get to some sort of representations. Okay, so weather is equal to sunny, cavity is equal to false. Some random variable can have weather is sunny, cavity is false, and then sunny or cavity is false. Okay, this has to be true, I guess, if this is the instance. So this is the instance of the random variable where every atomic clause is getting its instance value. So weather gets the value sunny, cavity gets the value false, and I can combine these two. So what they've done is they've actually combined these two together to have a compound statements. I can create compound statement using elementary proposition and standard logical connectives. This is what they say. So I can start with representing random variables. Some random variables may be Boolean, some random variables may be discrete. So I need to define those when I'm trying to represent the knowledge. Okay, domain values must be exhaustive and mutually exclusive. So these two things come in probability theory many a times. Exhaustive means they should cover the entire scope. That is, if I have a variable called as weather, either the variable could be sunny, rainy, cloudy, or snowy. Out of four, weather must be taking one of the value. There could not be a value which is different from these four values. So exhaustive means that. Exhaustive means the values that I am considering in the domain for a particular random variable, there can't be any other value the random variable can take. So discrete random variable में वो random variable exhaustive होना चाहिए, means it should cover all the cases. There could not be a corner case which is not covered by the list of values that are there in the domain of a random variable. Now what does mutually exclusive means? Mutually exclusive means if the weather is rainy, it can't be any of the other three weathers. So I should be able to say that weather is rainy today, and I should not see it is cloudy or snowy or sunny on the same day. So that is the meaning of mutually exclusive. The event of weather being rainy is mutually exclusive to the other three events, that is event of weather being sunny, weather being cloudy, or weather being snowy. And this is true for all the other cases as well. So this is the meaning of mutual exclusiveness. Exhaustiveness means all the type of weather should be covered in my domain, which represents the values for the weather. Okay, so I can't have a domain of values sunny and rainy for the weather domain, because the weather could be cloudy and snowy. So I have to have all those four values in my set, which is representing the domain of variable random variable weather. Once I have elementary proposition constructed by assignment of a value to a uh, random variable, so I can create elementary proposition. So elementary proposition का example क्या है? Weather is equal to sunny. So I'm assigning value sunny to variable weather, and I get a elementary proposition. Okay, and when I want to actually construct a complex statement, elementary proposition of two random variables, I just use logical connectives to connect it. So here these two, the number one here and number two, they are elementary propositions, and this entire thing is a compound statement that I have created using a combination of existing elementary proposition with the logical connective or. Here the logical connective uses or. Okay, so that's the syntax we are learning for the random variables that we use in probability theory to represent probabilistic behavior. Okay, so far we have not attached any probability number, but we are actually trying to understand how we represent things. So meaning के लिए so what in probabilistic logic, the atomic event means a complete specification of the state of the world about which the agent is uncertain. The complete specification of the state of the world means an atomic event. Okay, so now for example here they have considered that the world is consisting of two Boolean variables. One is cavity and the other one is toothache. So there are two Boolean variables here. One is cavity So